Okay guys, welcome back. So last lesson we talked about slopes of graphs, either slopes of v versus t and slopes of d versus t. The slope of v versus t is acceleration. Let's pretend these are graphs of d versus t. Which of these graphs shows an object that's moving backwards and slowing down? So it's going backwards, but every second the speed backwards is less. Which of these graphs represents that? Good job, it was number 4. 4 has a negative slope. In 1 and 3, the slopes are positive, but 4 has a negative slope, so it has a negative speed. So does 2. 2 also has negative slopes, but the slope in 2 is getting more negative, decreasing. 2 is speeding up backwards. 4, the slope is increasing, well, the magnitude of the slope is decreasing. The speed is decreasing. So it's getting slower and slower while still going backwards. So it's choice 4. Good job. Thanks, you did. Okay. So we talked a lot. Now we learned how if you had data of displacement versus time, you can graph it. So basically, there's a way to find velocity from displacement and a way to find acceleration from velocity. We're going to do the reverse today. And this is really important because you might get kidnapped, and it might be really useful to know how to do this. Let's watch an example.
Henchman for her to just have been followed from the moment the dude knows she was staying behind.
1, 2, 3.
Brian talks out the time, the directions, and what he hears instead of just keeping it to himself, but figures if the bad guys are going to let him make phone calls, they'll let him do anything. Kid in danger who's tired of waiting for the elevator will now conveniently decide to take the stairs.
A ja nuk është këtu. Nuk është këtu. Dhomën e babait.
Hotel to get the daughter? Then fuck, you have enough henchmen for her to just have been followed from the moment the dude knows she was staying behind.
1, 2, 3.
Brian talks out the time, the directions, and what he hears instead of just keeping it to himself, but figures if the bad guys are going to let him make phone calls, they'll let him do anything. Kid in danger who's tired of waiting for the elevator will now conveniently decide to take the stairs.
Okay, so in the movie, he gets kidnapped and thrown in the back of a van, and he can't really see outside, but he can feel the way the truck is moving, and he can hear some stuff outside, and he records how long they've been driving and tries to figure out where he is at every second, figure out where he's going, figure out where he ends up in relation to where he started from his hotel or whatever. So is that possible? Could that possibly be possible? How could you do it? Any ideas, Hazel? No. Okay. Well, I'll tell you. I'll help you guys out. Don't worry, I got you. Why is this necessary? Imagine you are blindfolded and thrown in the back of a van, and there's not all these weird noises outside, so you can't really hear where you are. Could you tell where you are by feel? No, that doesn't make sense. You can't feel anything outside the van, so you don't know where you are. Some people say, well, you can feel how fast you're going. Do you agree with that? Can you feel how fast you're going when you're in a van, when you can't see outside, can't hear outside? Are you able to feel how fast you're going? Tell me right now. What do you think, Sage? Can you feel how fast you're going? I think so. When I'm in a car and it goes fast, I can kind of push backwards. Yeah, I guess so. So if you're in a car and let's say I'm driving all my babies to daycare and I'm running late and I get in the car and I jam the gas and we're going 50 miles an hour, all the babies get pushed back into their car seats. Of course, I have 3 car seats. I'm a responsible parent. They all get pushed back into their car seats, right? Yeah. Daisy, does that make sense? Yeah, that makes sense. Well, what if we are in an airplane and again, I brought my 3 babies and I brought lots of earplugs also, and they strap into their plane seats and we take off going 500 miles an hour. Are you pushed back into your seat 10 times as much as in the car? Actually, no, Mr. Lamb, I'm not. Yeah, when you're in the plane, you actually don't feel pushed back at all, do you? No, you can get up and go to the bathroom and go harass some stewardesses, go run around, and then watch Frozen. There's lots of things you can do, and you barely feel the motion. That's true. It's a misconception. You can't feel your velocity. We're on Earth right now, and the Earth is flying through space at 30,000. We actually calculated this last lesson. 30,000 meters per second. You guys feel it? No, you can't. You can't feel your velocity. If you can't see outside and can't hear outside, you would have no way of knowing if you're in a van going 100 miles an hour or standing still. But you can feel acceleration. So in this movie, it would be very, very difficult. But if Liam Neeson could feel when his van accelerated and he could count the seconds he accelerated each time, in theory, he could figure out where he was at every single point while being kidnapped. Don't try it at home because it's a little dangerous, but it might, in theory, work. So let's pick a real simple example. Let's say he knew he accelerated. Let's say he starts out his motion. Again, we have the same thing before. Time in seconds, acceleration in meters per second squared. We have another table. How's the glare? I missed. Okay, it's fine. Okay, so let's make it simple. He starts out accelerating. He starts out accelerating 2 meters per second squared. And then he does that, the van does that for, I don't know, 10 seconds. No, I gotta find an eraser. I gotta be a little more clear. Okay, real simple example. They go at 2 meters per second squared for the first second, 2 seconds. Oh, I didn't need units because I already labeled the units on the top of the table. 2 meters per second squared, same. And then after 3 seconds, they stop accelerating. When you stop accelerating, does that mean you stop moving? What do you think, Sage? Of course not. You can be moving at constant velocity, and that's zero acceleration, but you're still moving. Wow, good job. So they keep on moving. He knows he stopped accelerating, but they keep moving for 2 more seconds. So that's a lot of data. Hopefully, when he was kidnapped, Liam Neeson had time to grab his calculator and his graph paper and his protractor, because to figure this out, you gotta graph it. So basically, they accelerated for 3 seconds. And then they kept the same acceleration. I know how you all want to draw this. You all want to go like this. That is not what happened. The acceleration at 0 seconds was not 0. It was 2 meters per second squared. Don't think acceleration has to start at 0. Velocity doesn't. Even position doesn't. You can start out at some random location that's not called 0. You can start out moving. You can start out accelerating. And that's what happened in this problem. He started with acceleration 2. Kept that for 3 seconds. Then his acceleration became 0. For 2 more seconds. Just because the acceleration is 0, we said, that does not mean he was not moving. He was still moving during these 2 seconds. We got to figure out how fast he was going, and then how far he went. So, we can do it mathematically, but we're going to learn the graphing shortcut right after that. So, velocity, time. I didn't really say it, but he would need to know how fast he was going originally. He was kidnapped, so luckily for him, he got kidnapped. You're probably thrown in a car that's not moving when you're kidnapped, hopefully. If you do, then I guess you have multiple problems besides just being kidnapped. And we are gonna start the graph at 0, 0. But this is assuming he knew he started at 0, 0. That's not necessarily true, but to make this problem work, I'll just tell you. You start at 0 velocity. He started in this velocity. He started at 0 velocity in this problem. So he accelerated 2 meters per second squared for 3 seconds. So this could be a quick problem that you could solve. V naught is 0 meters per second. A equals 2 meters per second squared. This is constant acceleration, so we can do the solution. Oh, I can't. Fixed. I fixed it. I'm great. And this happened over 3 seconds. Okay. Find the final velocity. Good job, you found it. It was 6 meters per second. 1, 2, 3, 4, 5, 6. And that happens at the end of 3 seconds. And as we learned last unit, what does a graph of velocity versus time look like if you have constant acceleration? I already have enough time marks. I'm kind of lazy. Oh, you guys can. Oh, this is really bad. Oh no, I just have to push it down. It's fixed. It's fixed. It's fixed. Okay, what do we say represents acceleration in a velocity versus time graph? Yes, the slope. So, if acceleration is constant, that means the slope is constant. So, bam. Here's my velocity versus time graph. A nice straight sloped line. From 0 meters per second up to 6 meters per second over 3 seconds. What happens after that? Zero acceleration, we said many times, does not mean no velocity. It means constant velocity. And for no reason, I want to make a dotted line back down to 0 here, because I said so. So now we're almost there. Our kidnapped guy figured out his acceleration over these 5 seconds. Now we figured out his velocity at every second for those 5 seconds. Now he's got to find his total displacement for these 5 seconds. How is he going to do it? Conceptually, this would be a good question. How do we draw a graph where the slope of this graph is the value of this graph? That would be a nice question for you guys, but it would be pretty tough. So we'll do it mathematically, the old-fashioned way for now. But I'm going to make this graph to help you guys think in the future. Well, we know we have to break it into 2 parts. There's 2 parts of this problem. I would make you guys set it up if you were in person, but right now I'm just talking to no one because there's no one in front of me, and I'm just kind of a crazy person talking to myself in my apartment all alone. So the first problem, find the displacement. Second problem, find the displacement. The first part, we start at 0 velocity. We same givens as up there. 2 meters per second squared for 3 seconds. Use physics powers. 9 meters. You can check my work if you want to, but I'm a genius, so don't worry about it. Second part, we know it's 2 seconds. It's from here to here. We need the final velocity of the first part. The final velocity of the first section is the initial velocity of the second section, and we already found it. We found it up here it ended up being 6 meters per second. And the acceleration is 0 meters per second squared. Good job, everyone. You figured it out. Use your physics powers. In this time, these 2 seconds, this kidnapped guy went 12 meters. So total 21 meters displacement. 21 meters of displacement in 5 seconds. Physics, we did it, hooray. But this lesson's supposed to be about graphing, so let's see if there's an easier way. Okay. To find the displacement, I use physics powers, but what you actually would do is do d equals v naught t plus 1/2 a t squared. Well, v naught 0, so this whole term is 0. 1/2 at squared, for no reason, I'm going to write it as 1/2 at times t. Okay, why did I do that? I was lying, it wasn't no reason. What's at? If you remember, up here, where it's cut off right now, at is 2 meters per second squared times 3 seconds. At is 6 meters per second. That is the final velocity. So this is 1/2 vt, where v is the final velocity, not the average. Why did I do all that? Use your big brain and look at this triangle. And tell me how this triangle and 1/2 vt are related. If you don't know why, I'll tell you after this. In the second part, same thing. We use d equals v naught t plus 1/2 a t squared. How's my time? It's 5. Well, in this case, a is 0. And v naught was 6 meters per second. And t was 2 seconds. And that 6 times 2, 12 meters, is how far the truck went in this section of the graph. Do you guys see the relationship? Do you understand how to find displacement from a velocity versus time graph? Can you put it in words right now? Great job. If you have a velocity versus time graph, the displacement is the area of the graph. Basically, you probably have a line as your graph, but you just got to draw like a dotted line down to the x-axis and just kind of fill it in. This rectangle, of course, it represents the displacement. Because what's the base of the rectangle? Time, 2 seconds, 1, 2. What's the height? It's the velocity. 1, 2, 3, 4, 5, 6. 6 meters per second. So this rectangle, its area is base times height. The height is 6 meters per second. The time is 2 seconds. So the area is 12 meters, which is the answer we got earlier. Wow, we are physics scholars, I know. We're the best. But does it work for weird triangles? Well, what's the formula for the area of a triangle? 1/2 base times height? Yeah, it is. Oh, thanks, Mr. Lamb. I knew I could count on you. You're welcome. 1/2 height is velocity. Velocity. Base is time. So 1/2 vt is 1/2 6 meters per second, 3 seconds. That's exactly what we have over here. 1/2 at squared is 1/2 vt. 1/2 base times height is also 9 meters. The area of this triangle It is 9 meters. So this is the trick to finding displacement from velocity versus time. The area under the graph, if you connect every point on the graph to the x-axis or the time axis, you'll make some kind of weird shape. If you have to calculate it, it would be something you know, like it would be a triangle or a rectangle or a trapezoid. But in theory, I could have any sort of crazy shape as long as the v versus t graph, all I have to do is find this mysterious area, and that will be the displacement of this object in this time period if this is the velocity. The area of v versus t is displacement. Okay, good job, me. Thanks. You might see something related in this graph too. This area, this rectangle, is a times t. We just said a times t is v, the final velocity. To be precise, a times t, or the area under these graphs, is actually change in velocity. But it's the same because in this graph, the initial velocity was 0. So it does work out just fine. This doesn't really come up as much. This is much more common. You might once in a while be asked to find the area under an a versus t graph, and if you do, it's the change in velocity, but it's very, very common to see, here's a v versus t graph, find the displacement based on this graph. And you might think, oh, I gotta find the acceleration and the time and the initial velocity and final velocity every single time. Nope, you don't. Just make a trapezoid or a triangle or rectangle or whatever, and find the area of that shape. The area of that shape, if you use the proper units and measurements, will be the displacement of the object during that time period. This graph, it's gonna look weird, so I'm not gonna do the calculations. I'm just going to kind of, wave my hands and it's gonna be magically done. But we know the slope of the graph is this graph. So for the beginning, the slope should be increasing. An increasing slope is a parabola. So for the first 3 seconds, I have a parabolic graph. Then here, does the slope of d versus t become 0? No, it's not 0. It's constant. It's 6 meters per second, not 0. So the graph will not go flat like that. It'll keep the same slope and go up like that. And then you'll reach some displacement, and bam, it's 21 meters. I happen to already know that because I'm a scholar. So that would be the graph of velocity versus time, but the area of this graph has no meaning, so don't worry about that. The only thing we need to know, area of v versus t is displacement.